Okay, let's just dive straight into this explainer. Today, we're uncovering the invisible and honestly totally incredible magic that lets our modern computers juggle a dozen tasks at the exact same time. We interact with these machines every single day, but we rarely stop to think about the crazy balancing act happening right beneath the surface.
So, have you ever actually wondered how your computer manages to play music, download a massive file, and run your word processor all simultaneously without just completely freezing up? I mean, to us, it feels totally seamless, but under the hood, it is this highly coordinated dance of resource allocation.
Right. So when you're just sitting there, casually typing up a document, your operating system is frantically managing all these background activities. It's downloading software updates, it's scanning your hard drive for viruses, it's streaming your favorite playlist, literally all at once. And doing this efficiently comes down to two foundational concepts in computer science: processes and threads. Section 1. Processes versus threads, the core building blocks.
Let's look at the process first. A program just sitting on your hard drive is essentially a dormant list of instructions. But the second you double-click an icon, say Microsoft Word or Google Chrome, it wakes up. The OS loads it into memory, and bam, it becomes a process. Now, the key here is that every single process gets its own secure, isolated sandbox. It gets a unique ID, its own memory space, and its own permissions. And because of this strict isolation, if one process crashes, it doesn't just take down your whole system or accidentally corrupt another app's memory.
But here is where it gets really clever. Instead of spinning up a massive, heavy new process for every single little task inside that app, applications use threads. These are basically lightweight execution units working inside the process. Take your web browser. It's loading a web page, playing a video, grabbing a download, and watching for your mouse clicks all at the exact same time. Instead of making resource-heavy new processes for all of that, the browser just spawns multiple threads that all live inside that one main process. And this table perfectly illustrates the contrast. Processes are independent programs. Threads are the smaller units inside them. Processes demand their own isolated memory, which makes them heavy and pretty slow for the computer to create. Threads, on the other hand, they share memory and resources with each other. That makes them incredibly lightweight, super performant, and just lightning fast to create. Basically, processes give you stability and isolation, while threads give you that crazy multitasking speed. Okay, let's use a real-world analogy to really make this stick. Picture a super busy restaurant. The physical building itself, the exact footprint, the locked doors, the dedicated kitchen, the tables, that represents our isolated process. It's got its own dedicated space that belongs only to it. Now, inside that building, you've got your workers, right? The cashier, the cook, the waiter. These workers are the threads. They are all working simultaneously to serve customers. But crucially, they're sharing the exact same kitchen and equipment. They don't each need their own separate building to do their jobs. And because they share those resources, the whole operation just hums along efficiently. Section 2. The process life cycle: birth, life, and termination. Every single app you open goes on this exact 5-step journey. When you double-click Chrome, it's new. Then it loads into memory and is ready. When the CPU actually starts crunching its instructions, it's running. But say it needs a web page to load. It'll actually pause and drop into a waiting or blocked state until that internet data arrives. Got the data? Cool. It jumps back to ready, then running. Finally, when you click the X to close the window, it's terminated, and the OS reclaims all that memory. Your apps are constantly bouncing back and forth between these states right behind the scenes. But here is the wild secret to the whole thing. A single CPU core can technically only execute one thread at any given microsecond. To make it feel like your music, browser, and word processor are all running at once, the operating system uses context switching. It pauses process A, saves its exact state, loads up process B, runs it for a split second, saves it, and moves to process C. It does this swapping so incredibly fast that, to our human eyes, it creates this flawless illusion of simultaneous multitasking. Now, to decide exactly who gets the CPU next, the operating system acts like a master traffic controller, using scheduling algorithms. First come, first served is simple, like a line at a grocery store. Shortest job first prioritizes the quick tasks. Round robin is super popular because it just gives every process a fair, fixed slice of time. And priority scheduling makes sure vital emergency tasks always jump the queue. The OS dynamically juggles all of these to keep your machine perfectly responsive. Section 3. Managing shared resources: when threads collide. Because sharing a kitchen or sharing computer memory can lead to absolute chaos if we aren't careful. If two threads try to update the exact same piece of data at the exact same millisecond, you get what's called a race condition. Imagine two employees frantically trying to update the same inventory record simultaneously. The count gets totally jumbled up, your data gets corrupted, and you get wildly unpredictable results. So, to prevent this data corruption, operating systems use strict synchronization tools to guard what we call critical sections of code. First up is a mutex, which stands for mutual exclusion. A mutex completely locks a single shared resource. Think of it like a single ATM machine. Only one person can use it at a time. The next thread literally has to stand in line and wait for it to unlock. On the flip side, we have a semaphore. This controls access to multiple resources. If an office has 3 available printers, a semaphore lets exactly 3 threads print at once. But that fourth thread, it has to wait until a printer frees up. But what if synchronization fails? Well, we hit the dreaded deadlock. This is the ultimate nightmare scenario. Process A locks down resource 1, but it needs resource 2 to finish. Meanwhile, process B has locked resource 2, but it desperately needs resource 1. Neither process is willing to let go of what they have, so they just end up waiting indefinitely for the other. The result? Your application completely freezes, and you're just stuck staring at an unresponsive screen. Section 4. Real-world troubleshooting. Why this matters. Okay, so why does all this invisible OS architecture actually matter to you? Because understanding the fundamental difference between a heavy process and a lightweight thread essentially gives you troubleshooting superpowers. When you open your task manager, it's no longer just a confusing list of numbers. You can instantly diagnose why a program is unresponsive. Maybe it's stuck in a waiting state for a network drive, or maybe it hit a deadlock. You'll understand exactly why a rogue process is eating up your CPU and why having too many heavy background apps just fundamentally slows down your system's context switching. Knowing this absolutely changes how you view your machine. You aren't just looking at a frozen screen anymore. You are looking at a highly complex ecosystem of processes and threads competing for resources. So the next time your application hangs and you instinctively hit Control-Alt-Delete, I want you to ask yourself, what exactly are my threads fighting over? Thanks for joining me for this explainer, and keep exploring the incredible architecture inside your devices.